Hi everyone, and welcome to this tutorial session. In today's tutorial, we have the polynomial g of x given as x cubed plus x squared plus 2x plus 2, and the rational function f of x given as x plus 2 all over g of x. To first show that x plus 1 is a factor of g of x, and then next b to express f of x in partial fractions. All right, let's start. Please watch the solution carefully because a lot of insight will be demonstrated in all the major steps of this solution. We are given g of x, the polynomial g of x as x cubed plus x squared plus 2x plus 2, and the rational function f of x as x plus 2 all over g of x. The first thing we're asked to show that x plus 1 is a factor of g of x. G of x is a polynomial of degree 3. All right? So we have to show that x plus 1 is a factor of g of x. There are two methods. Let's take the first method. Method 1 is by Euclidean division. All right? We'll carry out Euclidean division, and if we see that the remainder is 0, then it confirms that x plus 1 is a factor of g of x. If the remainder is not 0, then x plus 1 is not a factor of g of x. Now let's do that quickly. All right. We have x cubed plus x squared plus 2x plus 2. Carry out this Euclidean division. So what are we going to write here? Up here, just above x cubed. It should be an expression such that when we multiply back, we're going to have x cubed here. Remember, we're going to do subtraction, so that we'll end up with a 0. We should at least have a 0 in the first column. So what expression should we write here? Such that when we multiply back, remember, we're going to multiply by x and also going to multiply by 1. So what we can write here is just x squared. So that x squared multiplied to x will give us x cubed. All right, so that when we do the subtraction, x cubed minus x cubed, 0. All right, so we'll carry out the multiplication here also. X squared multiplied to 1 is x squared. It just happens here that this one minus this is 0, this minus this is 0. They are the same expressions, so everything is 0. It's not going to be like that in all polynomial division, so you should take note. This is just a case where it just happened that we have 0 and we have 0 here. All right, now we'll bring down this. This is 2x. We'll bring down this also, plus 2. Okay, so what are we going to write here? This is positive 2x, so we'll write positive. What are we going to write here? So that when we multiply back, we're going to have 2x. Remember, we're also going to do subtraction, and we need to have a 0 here. This first column should at least be a 0. The other one may not be 0. All right, we want to obtain a 0 here. What are we going to write here? So when we multiply back, we're going to have 2x. It should be 2. 2 multiplied to x, 2x. So you can see 2x minus 2x, 0. But 2 multiplied to 1 is positive 2. Again, we obtain 0, 0. So finally, our remainder is 0. We have carried out the Euclidean division with x plus 1, and we end up with the remainder 0. So this confirms that x plus 1 is a factor of g of x. That is method 1. Method 2, is factor theorem. Factor theorem. What does the factor theorem say? It says if x plus 1 is a factor of polynomial g of x, then first thing, you set x plus 1 to 0 and you solve. It means x equals negative 1 is a root, which also therefore now means that g of negative 1 must be 0. Okay? If x plus 1 is a factor of g of the polynomial g of x, then g of negative 1 must be 0. -1 must be a root or a solution or a zero of that polynomial. So let's verify to see if g of -1 will give us 0. Remember, this is g of x. That means in the place of x, we're going to put -1 here. Wherever we find x, we put -1. All right, so that gives us -1 cube, -1 square, 2 multiplied to -1 plus 2. -1 cube means -1 multiplied to -1 multiplied to -1. This one, -1 cube. So negative times negative, positive times negative, negative. So this one here is -1. -1 squared is +1. Then 2 multiplied to -1, -2 plus 2. This is 0, this is 0. So everything gives us 0. All right. So we have shown that x plus 1 is a factor of the polynomial g of x using the factor theorem. That does it for the first part of this question. Second part is express f of x as partial fraction. Express f of x as partial fraction. Now this is f of x. It is equal to x plus 2. Earlier on, we found that x plus 1 was a factor of g of x. And when we carry out the Euclidean division, we had x squared plus 2. Okay, x squared plus 2 as the quotient. So this g of x factorized out as this. Now, this is a linear factor. It's already in the reduced form, but this one is a quadratic factor. All right, can we reduce it further? Can we get 2 factors? Because a quadratic expression must have 2 factors. Is this quadratic reducible? Let us check. All right, let us check. Our a is a coefficient of the x squared term. Our b is a coefficient of x term. There's no x term there. And our c is our constant term. Now, the discriminant is b squared minus 4ac. Let us check the sign of the discriminant. Remember, the discriminant is what is under the square root sign. All right. If the discriminant is negative, you see square root of negative values don't exist. But if the discriminant is positive, it means that this quadratic expression is reducible. We can factorize it to have 2 other factors. So let's check the discriminant to get its sign. B squared is 0 minus 4 into a into 2. This gives us -8. All right, so discriminant is negative. Square root of -8 is not a real number. So we don't have real roots. So this quadratic expression is not reducible in the field of real numbers. It's not reducible in the field of real numbers. So what therefore is the method now to express this as partial fractions? That method will be f of x expressed as a all over the linear factor plus bx plus c all over the non-reducible quadratic. Okay, right? F of x must have that nature. So we need to get the values of a, b, and c. All right, how do you go about that? Remember, f of x is f of x. So we're saying x plus 2 all over x plus 1 into x squared plus 2 is a all over x plus 1 plus bx plus c all over x squared plus 2. All right, look at it. This is the product of this denominator. So this is like the LCM. So it will multiply all through by that LCM. All right, we'll multiply here by this same denominator. It will cancel itself and we'll have x plus 2. We'll multiply this first rational expression by this same LCM. X plus 1 cancels x plus 1. We're left with x squared plus 2. So we'll have a into x squared plus 2. The same thing, we'll multiply this one by the same LCM. X squared plus 2 cancels x squared plus 2. We're left with x plus 1. So we'll have b x plus c. This time we must put parentheses into x plus 1. We'll put that one in parentheses. So let me write it in a neat manner here. So we're saying x plus 2 is equal to a into x squared plus 2 plus bx plus c into x plus 1. That's the expression that we have. This will help us to calculate the values of a, b, and c. Quickly, if we look at it, we see here that if we put the value -1 for x on both sides of the equation, -1 plus 1 will be 0. 0 multiplied by all of this will be 0. So we'll have only one unknown, which is a. So that will help us calculate the value of a. Let's go ahead and do that. Put x equals -1. All right. So the left-hand side, we have -1 plus 2 is equal to -1 squared is 1 plus 2 is 3. So have 3a plus 0. Because -1 plus 1 is 0. 0 multiplied by all of this is 0. All right. So we're having 1 is equal to 3a. If we divide both sides by 3, this means a is 1/3. All right. So we found the value of the first constant a. A is 1/3. Now we found the value of a. How do we get the other values? B and C, how do we get them? We see B is multiplied to X. So from common understanding, we see that if we put the value X to be 0, B will be eliminated. We'll end up with a new equation involving A and C. And we already know A. So the only unknown will be C. So that equation will help us calculate the value of C. So we'll go ahead and say, go ahead now and we say put X equals 0. Okay, we're working with this. We're working with that. Put X equals 0. So have 0 plus 2. We're going to have 2. 0 squared is 0 plus 2. So have 2a. 0 multiplied to b, 0. Then we'll have c. 0 plus 1 is 1. 1 multiplied to c is c. All right, and we know a. A is 1/3. We'll come and put it there. 2 is equal to 2 into 1/3 plus c. 2 multiplied to 1/3 gives us 2/3. So to get c, we simply carry this one from the right hand side to the left hand side. So we'll have 2 minus 2/3 will give us c. So what do we get there? This is, we can also make this like that to have a fraction. So the LCM is 3. 3 divided by 1 is 3, multiplied to 2 is 6. 3 divided by itself is 1, multiplied to 2 is 2. So this gives us 4 all over 3. So the value of c is 4 all over 3. All right, so now we know the value of a, we know the value of c. We need to get the value of b. That should not be a problem. So let's expand the right hand side and we equate coefficients. Okay, so let's expand the right hand side of this expression and we equate coefficients. So this is the same expression, the one in the box, we're working with it. So we're saying x plus 2 is equal to, open out this, we have a x squared plus 2a plus, multiply this out, bx multiplied to x is bx squared, bx multiplied to 1 is bx, c multiplied to x is cx, c multiplied to 1 is c. So let's arrange things. Let's take the x squared coefficients. X squared, we have a, we have b. Then let's take the x. X will have b and we'll have c. Then the constants, 2a plus c. Okay. We already know c and we know a. We already know c and we know a. We know that a is 1/3. We know c, we know a. So we have this quadratic, the right hand side is a quadratic expression and the left hand side is linear. So if we are saying this is equal to this, it simply means that the coefficient of the x squared term must be 0 because there's no x squared term this way. So if we equate corresponding coefficients. Equate corresponding coefficients. It therefore means that we have for x squared term, we have 0 is equal to a plus b. 0 is equal to a plus b. So from here, we now see that b is just negative a. So b is negative 1/3. So the value of b is negative 1/3. All right. But if we took the x term, let us see if we take the x term, if we'll get the same result if we took the coefficient of x term. Let's take x term. On the left hand side, the coefficient of x term is 1. On the left hand side, the coefficient of x term is 1. On the right hand side, this is the x. The coefficient of x term is b plus c. Let us see if we will still obtain b to be negative 1/3. So this is b plus our c is 4 all over 3. So this is what we get. So we're saying b will be, take this one, this will be 1 minus 4 all over 3. I'll write 1 also as a fraction. LCM 3. 3 divided by 1 is 3, multiplied by 1 is 3. 3 divided by itself is 1, multiplied by 4. So this gives us negative 1/3. So b is negative 1/3. Therefore, f of x as sum of partial fractions. F of x as sum of partial fractions will be a is 1/3 all over x plus 1. B is negative 1/3 x. C is 4 all over 3. Now, this simplifies to the 3 comes down. We'll have 1 all over 3 into x plus 1. And then this one there, negative 1/3 x plus 4 all over 3. LCM is 3. 3 divided by 3 is 1, multiplied there is negative x. 3 divided by 3 is 1, multiplied to 4. So this can also be written as 4 minus x all over 3. So we have here 4 minus x all over 3 into x squared plus 2. All right, so f of x expressed as sum of its partial fractions will be 1 all over 3x plus 1 plus 4 minus x all over 3 into x squared plus 2. X squared plus 2.